This is the Amp Hour Podcast, released May 27th, 2019. Episode 444. An interview with Ben Eater. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Ben Eater.
Hey, Ben, how you doing?
Good. How are you?
I'm good. People probably know you from your videos about 8-bit computing and breadboard computers and all that other stuff, right?
That's a thing that I'm known for.
That is a cool thing, and we're definitely going to be talking about that here. What else generally do you do? I mean, so you're software and hardware, mostly software. What are you doing these days?
Yeah, probably mostly software is certainly my background, and actually networking as well. So I spent maybe 15 years in the networking industry. But lately, yeah, it's mostly been software, and then this 8-bit computer YouTube thing has been more of a side project.
Yeah, I'm sure people. So first off, if people haven't seen it, it's eater.net is your site, and then the tutorials are all YouTube based. So maybe we start with that. Like, first off, how did you start getting into this? Because it seems like it kind of builds on itself. But how did you start doing it, and what was the basis for starting to do the computing stuff there?
Yeah, so I guess, I mean, as a kid, I was always kind of into electronics, so it had always been a hobby for me. I think, like many people, I'd went to Radio Shack as a little kid and drooled over all the little components, and got as much as I could, brought it home and tinkered. And then my career path didn't end up going down the hardware route so much, but it had always been kind of a hobby. And even in high school, I guess I started doing more kind of computer systems-y things in terms of building hardware that I could plug into my computer. Whether that was parallel port stuff to turn on lights and do different things, or even building like an ISA card interfacing with the old 8-bit bus in the old PC architecture. And so from that, I had kind of this sense of how a computer worked and how the computer architecture worked. And so it had always been this kind of idea in the back of my mind that, like, I bet I could build a computer from scratch, where scratch is like logic gates.
Right.
And so it was always something that I kind of imagined doing someday. And then, fast forward 30 years or whatever it is. And I had some time and kind of had an idea and decided to try to do it.
That's great. And so, okay, let's kind of walk our way back through. I mean, so you go over some of the, gate stuff, and obviously you have a lot of educational content. We'll talk about education a little bit later. Yeah. But I mean, where does one start when starting to build a 8-bit computer from scratch?
Yeah, so I guess where I started is I had come across this book a while ago called Digital Computer Electronics. I think it's out of print, but the author is Albert Paul Malvino. And it's an amazing book that describes CPU architecture, from logic gates essentially, and goes through a lot of the same things that my videos go through. And so that kind of gave me this idea of, like, okay, here is a tangible thing I can kind of get my arms around. And in that book, he describes this architecture he calls the SAP1, which is simple as possible. Which is what it sounds like.
I don't know that one. It's but yeah, okay.
It is as simple as possible as you can make a computer architecture, which is roughly what I ended up doing in the videos. It's tweaked a little bit and so forth, but
okay.
But that's roughly the architecture that I used. And so I built something roughly along that architecture. It was actually for a hackathon, so it was a really long, like, I think 4-day weekend-ish, but like 12-hour days for 4 days straight. Just hardcore.
Red Bull,
lots of Red Bull, lots of caffeine for sure.
Yeah.
And by the end of it, I surprised myself. I had something that was kind of working as a computer. And my goal was that at some point this could be a series of videos, or I guess at the time I thought a video describing how it worked.
So young. So explaining it all in a single video.
15 minutes should do it.
Yeah.
Right?
Oh, geez. Yeah. Most
And so
professors,
actually,
what are they even doing out there with all those hours and hours, right?
I mean, it's simple as possible. How hard
Yeah.
could it be, right? And so
How long
actually,
is this
when I was
book? How long is this book that you used? And it's like
it's a
400
couple
page
hundred
book.
pages, yeah.
Yeah, yeah.
But yeah, but and so actually, when I was building it during the hackathon, I had a camera pointed at me, recording it because I
Oh,
figured, oh, I just
great.
get all this footage and then I just edit it together and throw together a little narrative, and will be one nice video describes how a
Right.
computer works. Everyone will love it,
Awesome.
and that wasn't going to work at all. So after I built it, I started making some other videos about how a 4-bit adder works and building that from logic gates, and it's kind of some smaller components. And I
Yep.
guess at some point came to the conclusion that maybe that was the way to go, is just to talk component by component and almost show building each one.
Yeah.
And so what I did is said, I'm going to start over. I'm going to build a second one from scratch and
hmm
make videos showing that process from start to finish. And that's ultimately what I ended up doing. And it took, I don't know, 3 or 4 years
Yeah.
and
Well, and
over
because you're
40
filming
videos.
and right, exactly. Yeah, you got all that other stuff, all the overhead there too.
Yeah, yeah.
It's
And a
tough
day
too
job.
because I mean, like, what do you? Well, yeah, money, blah blah blah.
Yeah, yeah. Details.
Like when you think about, and I'm sure you got a lot of feedback from people too, but like, where do you usually start? Like when you think about starting with a computer like this, do you think about people coming at it from the software world or the hardware world or the transistors bottom up type of thing or software top down? Where do you think about it personally, and then what do you think is the best method for approaching education like this?
Yeah. I mean, I think personally, I just thought about it from, 14-year-old me.
Okay.
And I just kind of imagined, what would I have wanted to see when I was 14, given what I, remember I thought I knew when I was
Right.
that age. And that's kind of how I approached it. And so I made some assumptions. I don't really explain how binary works at any point in the video series. So I assume you
Right.
know
Yeah.
that. I don't
hmm
really explain a lot about, I mean, I don't talk about Ohm's law, for example. I don't really go into any of that sort of more basic stuff. And arguably you don't even need to understand Ohm's law to understand how a computer works, which is kind of funny.
Yeah, that's kind of
Um,
crazy, huh?
but I, yeah, but I guess I just kind of had this mental model in my head of who I thought was watching it, and that was roughly modeled after me when I was like 14, and and that's kind of who I felt I was speaking to,
hmm
and it happens to have resonated with a lot of people.
That's great. That's great. And so, I mean, and you mentioned kind of breaking it down into the component parts. What were some of the things that you felt like you had to kind of go over as like an understanding kind of thing? Because I should say, 14-year-old me had no concept of computing at all. I didn't do anything like that. I didn't actually get into it until college, and then it was actual instruction from a professor. And at that point, it was
Sure.
very like, let's do Carnot maps and let's do transform and De Morgan's theorem. And it's like, but at a certain point,
Right.
like what you're talking about building a real thing. And I'd really like that hands-on practice. Obviously I like that hands-on practical approach. That's what, I always talk about, but, um, you know, what made you decide then to like, oh, this one actually deserves some more like diving into it? And like, what were some of those topics?
Yeah, I guess again, I thought about it from the standpoint of I want to get to a point where at the end of it, I feel like I understand how it all works, but I didn't feel bad about cutting any part out that I didn't think was strictly necessary.
Mm-hmm.
And I think a lot of it's a judgment call. Carnot maps, for example, don't talk about that at all. Um, there is one video where I go from a fairly complex combinatorial logic thing, and then talk about how you can recreate that in an EEPROM as a
Mm-hmm.
lookup table. And there's a perfect place to slide in Carnot maps, however you say that.
Yep.
But I was just like, you know what? It doesn't matter. Like, you don't need to know that. And
Right.
if you then go on and take a class where you get into that stuff, you're going to have a lot of context for why that might be useful or how to use that or what have you. But
Right.
it's
It'll
not
give you the
essential.
motivation to actually like keep learning and digging in instead of being like, oh, this is just a math thing I have to do or a logic thing I have to do.
Yeah, exactly. So I think I wanted to cover what I felt you would need to cover so that for any, I guess, any potential sort of why question you might ask as you go along. So you're like, why does that work? Or why did you do that? Or I try to sort of anticipate any of those sorts of questions that you might come up with and try to answer those. but maybe not stray too far beyond that.
Yeah.
Um,
Yeah. Okay.
again, kind of thinking about that model. 14-year-old me, the person I'm sort of thinking of in my head as the audience of like, what would that person be interested in?
Sure. Yeah, I mean, and like you go over semiconductors and transistors and all that stuff too. Um, uh,
And I think that starts from that why, because
yeah,
I feel like if you start from a logic gate, you're like, well, why does that work? How does that work? It's like, well, it's made of transistors. Like, well, why? What's a
yeah.
transistor? How
What
does that
what
work?
is that? What? Yeah, right, right.
Yeah. And then then I get down to chemistry, and it's like, okay, that's someone else's problem. Explain that.
Right,
but
right.
but
Yeah, I
yeah,
mean,
it's just sort of
yeah,
like
it's.
working backwards.
Mhm. Yeah, so from that perspective, it is kind of like a top down ish because you're saying like this is a computer, people can kind of grok what a computer is, but now we're digging into each individual component, and you need to understand why there is, like you're just like even saying memory units and individual like storage elements of a single bit of memory and stuff like that. That's like a flip flop, right?
Yeah.
And so I could see that's why you're kind of talking about different flip flop types and low level things like that.
Yeah. I mean, I guess I think about it top down in sort of planning how I go through it, but the
Hmm.
video series ended up being bottom up.
Sure. Oh yeah. No, I think
Yeah.
on a
Yeah.
broad scale, it's definitely bottom up because it's like, well, this is like the basis of, you know, hell, the servers that we're talking through right now, right? There's at the bottommost level in very very tiny transistors. There's similar things happening, all around us
Right.
every day, phones, whatever. So
Yep.
it is bottom up from that perspective, but there's always a lower level you can get to, right? You could go and talk about like you said, the semiconductor physics and even the electrochemistry and all the things that down the rabbit hole, right?
Yeah.
But
You could keep going down, but
right.
I think, I mean, generally the way that I structured it, I do start at the semiconductor level, um, but then I work up. Okay, how do you build transistors from a semiconductor? How do you build logic gates from transistors? How do you build a latch from logic gates? And then how do you build a
Yeah.
register from latches? And just kind of keep going up, and then once you have like, okay, here's a register and here's a counter and here's these different memory module and all these things, then it's like, how do these things fit together at a system level
Yeah.
to form a CPU?
Yep. Yeah. Yeah, that's good too. I mean, so do you think broadly that this has impact for people these days? I mean, like software programmers, should they know this kind of stuff?
That's a good question, because I mean, a lot of software programmers don't know this stuff and seem to
Yeah, I
be
mean, you
doing
have
all
someone
right.
writing JavaScript or Python or whatever. Like, how often do you really thinking about the hardware that's on the bottom level with like all those layers of abstraction there? But
Pretty
maybe it's
rarely,
useful.
if ever.
Yeah. Yeah.
But I mean, I find that it's interesting because I see comments obviously from viewers, and a lot of them are software engineers who are in that position of, I've never understood this, and this is fascinating because I work on computers all day, and so they have some notion that, yeah, there's this high level language they're using, and yeah, that compiles, or it's interpreted by something that's then compiled into this assembly language or machine code, but then that's sort of where it runs out for them. And to
Right.
see from the hardware up, because that's kind of where my video stop is. Okay, now you've got machine code.
It's interesting too. There was that. Do you remember that mega computer that was? It was like I think a
Yeah.
British person was doing
Yep.
that a while back. And I remember saying like, I don't really think this is useful. Like what is the real point of this? And then it was like a couple of weeks or months after that, I was doing some C stuff and I was just, pushing stuff around registers and doing pointers and whatever. And, as you get closer to the hardware though, really having if not a direct grasp of the exact architecture you're working on, at least a general one of like, oh, well, how is this data chunking through the system? It, it can definitely have some impact, especially as you get closer to the hardware. I don't know if you've seen the same thing.
Oh yeah, for sure. I mean, definitely, if you're doing C programming, you are thinking, or at least occasionally, about registers and register transfers and kind of what's happening at that level. And yeah, to understand what's going on in the hardware and what that actually means. And obviously, especially if you're thinking about any kind of assembly language,
Hmm.
understanding
Yep.
what it means for an instruction to take a certain number of clock cycles.
Right.
If you've gone through my videos, that's pretty obvious what that means.
Yep. Yeah, and I think it's it all comes down to like the choice of the user. I think at the end of the day, like how deep do you want to go? How far down the rabbit hole do you want to go? Like if I think about even just playing around with an op amp, like, which is something I've done a lot in my life. I
Yep.
don't really think about the internal structures in there. Right? I don't think about the protection diodes until they jump up and bite me in the ass because of some, corner case that I'm dealing with or something like that. But I guess having like at least a cursory overview of it does help in certain ways, in certain like scenarios. Maybe not for the Python programmers of the world, but maybe as they dig down into it.
Yeah, maybe. I mean, that's the thing is like we depend so much on abstractions so that you can
Yeah.
be a Python programmer and not have to think about any of this stuff. But every abstraction, no matter how hard we try, is leaky in some way. We obviously try for that not to be the case, but even if it just in terms of performance, you're always going to have some kind of leaky abstractions. And so the better you understand what's on the other side of that abstraction, the more intelligent decisions you can make with what you're doing.
Yeah.
Yeah, it's kind of hard to make the case for understanding computer hardware and for a Python programmer, but because there's a few levels of abstraction between there. But
Right. When I think about like I've been doing server stuff lately too, and like virtualization and stuff like that, and now it's like
oh yeah,
even at the computing level, I mean, you do a lot of networking. I'm sure you do a ton of that stuff, right? It's like
sure,
now
yeah.
there's just like layers and layers and layers, even on top of the software, and it's kind of crazy. But it's also from the perspective of getting stuff done and having a lot of resources at your disposal. That stuff is kind of necessary to move quickly and efficiently.
Yeah, sure. And I mean, I think the more you know, it's just more data points that you can kind of synthesize as you're solving problems. Doesn't hurt,
Yeah. Yeah.
especially if you find it interesting.
Yeah, definitely. Well, I'm wondering if you want. Now, this one is obviously people should watch the videos, but I was wondering if you wanted to do a little word picture with me here and walk through the data path of a computer real quick. And I don't know if that would work at all here, actually, but maybe if you would walk people through, like, okay, so you push data into a computer like this, and it chunks through, and you're trying to light up LEDs at the end. Where does the data go? And if you're trying to, add stuff together, maybe.
Yeah, I don't know how to do this without a visual.
A word picture. I know exactly.
Word.
Well, like, and this is maybe it's not a good move. I mean, I think broadly, I think about like RAM and ALU as like these high level things, and you break them down as more as well, like how they actually work. But like kind of like putting things into operating memory and then pulling it back out in order to add them together, stuff like that. Did you operate from? When you were thinking about writing all these things and doing all these tutorials, were you doing it from like an assembly language perspective almost, or was it more just single operation and single instruction type stuff happening?
Yeah, I guess building the computer, I'm thinking about it from the micro instruction level.
Mm-hmm.
And so micro instruction is, well, I don't know, maybe it would help to step back and try to do what you were suggesting with this word picture of
Okay,
how data
yeah.
flows.
If it doesn't work, I mean, obviously people have the backup of just sitting there, okay, go watch the video. Like people should be watching the videos anyways, but it's
Yeah,
kind
check
of
out
fun
the
to do
videos.
this sometimes. Yeah.
Yeah, but I mean, I guess if I were to sit down, so let's say we build this computer that I've built in these videos. I want to sit down and program it to do something. Um, it's pretty basic. It has 16 bytes of memory. It's not the most advanced computer in the world, but
Right.
with those 16 bytes of memory, you can use those each memory location either for an instruction or for data, and it's entirely up to you. There's no segmentation or anything. But you program it with dip
Right.
switches. So you'd set the memory address dip switches to zeros, 0000, and then you can set the data dip switches to whatever bit combination for whatever instruction you want it to execute.
Mm-hmm.
And then you hit a button, and then that'll manually program that into that memory location. And then you do that for each memory location for your program. And there's different machine language instructions, which are encoded as different binary values. And those are the things that you're programming in that memory. And then when you actually switch the computer into run mode, so it's going to run through that program, each instruction essentially has kind of two stages. There's a fetch stage where it's fetching the data from memory and decoding it. And then there's the actual stage where it does whatever that instruction says to do.
Yep.
I don't know if you're following along so far.
I am, yeah. This is great. This is really great. Yeah. And I think like even just from the start, right, where you like there's there's an instruction and there's data, and like that alone is like, oh right, of course, there's like, you have to have the thing that you're operating on and then the operand that you want to do to it. Like those are but like those are kind of base level things where if you just assumed you knew all that stuff, maybe, or you assume that people knew that, they might not, you know what I mean? Like that
Yeah.
there are these different things and then one interacts with the other.
Yeah. And in this computer, for example, there's 16 bytes of memory. So there's only 16 8-bit things you can put in memory. And each of those 8-bit things could be an instruction or it could be data. It depends.
Right.
Typically, the thing in address 0 is going to be instruction because when you reset the computer, that's what it starts executing. But it might, execute something in address 0, then it'll move on to address 1, address 2, address 3. Maybe it'll loop back to address 0. And so then address 4, 5, 6, and so on, those could be data, or they could be unused, or who knows.
Right.
So what a particular memory location is used for is, not necessarily known. Now, some computers have segments that are for executing code versus data, and that's maybe a good security thing to do, so that you don't accidentally execute user data.
Right.
But
right. Injecting bad stuff in there or something.
Yeah. But that's not a thing that I'm doing on a breadboard.
Right. Right. So we're gonna do a security audit now.
Yeah. Well, there's no speculative execution attacks. Immune from those.
Yeah.
No Spectre bug.
Right.
But yeah, so I mean, the computer itself, I mean, most of what's going on is you're just sort of moving data from one register to another. That's really a lot of what it is. And so
Right.
you have some number of registers in this computer. Well, it depends how you count, 2 or 3 or 4, but the registers are hooked into a bus. And then at any point in time, a register can either be spitting its content onto the bus, or it could take whatever's on the bus and read it into that register.
Mm-hmm.
And those are just control signals. So each register has a read and a write control signal. It's either high or low. And so if the write control signal is high, then whatever's in that register gets put on the bus, and then everything else that's connected to the bus can see that value. And obviously, you want to make sure there's only one thing at a time doing that, because you don't want multiple things writing to the bus at the same time.
Yeah.
And then you have the read, which says, if that read signal is high, then that particular register will just take whatever's on the bus and read it into that register on the next clock pulse.
Yep. Yeah.
And so
then using the registers, actually, that's like the kind of like the working memory area effectively, right? I mean, that's like how you interact between different pieces of data that you're pushing around.
Yeah. So if you want to add 2 numbers, you'd load one of the numbers into one register and you load the other number into another register. And then depending on how the computer is set up, you probably have those 2 registers connected via hardware into some arithmetic logic unit that can do the addition. And then you can tell the ALU, like, do addition and put the contents on the bus. That's how you get the result out of that. And then you can take that result and read it into another register.
Yeah. What is the and I think we should, is that the end of the process, you think? Or I mean, I guess you're adding, subtracting, kind of manipulating data, moving it around. Are there final outputs to that kind of thing, or what?
Yeah. So in my computer, there's an output register, which is a little bit different than a real computer, I guess. But there's a register that if you put any data into that register, it'll show up on a little LED display, a little 7-segment display.
Mm-hmm.
That's good. In a sort of quote unquote real computer, you might have a video card, and so in that case,
sure. Yeah.
I guess a simple example might be the video card might be memory mapped. So what you do is you'd write data to particular memory addresses, and then the video card is kind of reading that same memory, and whatever contents is in that memory is what it's painting on the screen.
Yep.
But again, it's still just kind of register transfers.
Right. Yeah. When you really break it down like that, it's kind of crazy. You think about how all that stuff shifts together, and that's what makes video games, and that's what makes, audio transfer over networks, and like all the things
really fast.
Yeah, exactly. Yeah. So that kind of brought me to how fast are we talking about here? Like, what is the speed of this thing?
Well, I mean, you can go a couple hundred hertz, which is not too impressive. In reality, though, just because you want to be able to see what the output's doing, like, you probably only run it at a couple hertz because it's an educational thing.
Sure.
but it's also on a
can
bunch
you
of
single
breadboards.
step as well? Can
Yeah,
you
you can
single
single
step?
step. Yeah, you
Yeah.
definitely often want to do that.
Yeah.
To sort of trace through what a program's doing. And
Hmm.
so I have a video where I do that. I step through a program.
That's great. Yep. Yeah. I mean that kind of stuff too. It's like I think that this is a really good way to think of, like as people are thinking, kind of moving up that stack of hardware up to machine code, like you're talking about. These are effectively machine codes, with the different instructions and things like
Yeah,
that. Then there's assembler that would kind of put those together, and then maybe you have C on top of that. That's actually writing the assembly and stuff like that. Um, that sounds right, right? And then maybe C can also be Python up above that or whatever.
yep,
Um,
yeah, pretty much. And then the C compiles to assembly, or well,
mhm.
yeah, or machine code. I guess you can write assembly and assemble that into machine code, or the C
Yeah.
compiler will compile to machine code. And then
Mhm.
the machine code instructions are made up of micro instructions, and that's actually kind of the hardware that you're doing. Is each instruction has some number of micro instructions that make it up. So, for example,
Mhm.
if you wanted to add a number, the first micro instruction might say, uh, "Turn on the output from memory and turn on the input from the A register." And so what
Mhm.
that'll do is it'll
Yeah.
move data from memory to the A register. And then the next micro instruction might say, turn on output from somewhere else and turn on input to the B register. And that'll move data from somewhere else into the B register. So now you've got the two operands in the A and B register. And then the third micro instruction might say, take the output of the ALU, which is now your sum, and turn on the output of the ALU, turn on the input of the A register. So that'll move that sum back into the A register. And so those are those micro instructions that make up an add instruction. And so the machine
Mhm.
code would just be one instruction that says add, and then that machine code is defined to take data from these different places and add them and put the result in some other place.
Right. Yeah. And I think that's the other thing. I remember like one of my first classes in writing, I think it was writing C++ too, and decently high level language, I suppose. But it was just like I had no concept of what was going all the way down to the bottom, right? And
Right,
I don't
right.
think it was even. I think it was running on like a 486 processor or something like that. Anyways, probably an Intel something. And so like there was no concept of what was actually happening, and it was just so far away from what you're talking about. But I like that like what you're talking about there is you're talking about actually writing 1+1 equals result, and then
Yep.
it actually is implementing each of these different instructions and micro instructions and stuff like that.
Yep.
What does it look like when instruction actually hits the computer? Right? Is it just like a pathway that is pre-programmed based on logic? So like if the instructions 0, 1, then there's a like a effective logic pathway that kind of is activated by that 0, 1. What is the actual implementation of an instruction or micro instruction that then makes it do the thing?
Yeah. So you have essentially kind of a couple. You can think of it as like a combinational logic circuit that has some inputs and some outputs. And the outputs are the control, or what's called the control word. And the control word is really just a whole bunch of control bits that are things like, you know, uh, put the contents of the A register on the bus, or read what's on the bus and put it into the B register. Each of those would be a bit. So a register would have two control bits, one that says read, one that says write to or from the bus. And so you have a whole bunch of control bits. In my computer, it's, what is it, 16 control bits. In other
Mm-hmm.
computers, it might be 100 or more, just controlling all of these different things. And so at each point in time, that set of control bits tells all of the different parts of the computer what they're doing. So that's the output of the decode logic. The input of the decode logic is the instruction that you're executing, which you fetched from memory, and the step that you're on. So there's essentially a little counter that goes through, 0, 1, 2, 3, 4, and so forth. And so for each instruction, you could be on step 0, you could be on step 1, you could be on step 2, and you get a different control word for each step. And those are the
Yeah.
micro instructions. So
Right.
the decoding is really just combinatorial logic, where you're, or combinational logic, whatever the right term is, where you have the instruction and the step coming in on one side, and you have this whole control word going on the other side that's
Mm.
controlling everything.
Right. Yeah, and I think
And
about like the control word. You think about it like you look at these things, and it might be like 0xBE or something like that. Usually reading in hex or whatever.
yeah,
But like you're saying, yeah, you break it down into binary, and then you're like, oh yeah, bit 4 controls that thing. And
Yep.
then it's
Yep.
flipping on or off, and it's doing that thing or opening that pathway or whatever it is, putting
Yep.
stuff under the bus like you're talking about. And that is ultimately um, the output of this thing. I like that. I like that a lot. And when I think about like writing drivers for like in C for like a spy chip that you might be working with, oftentimes it's that same thing. You're going through, you're reading the data sheet, you're like, oh, pin 6 does enable heater or enable you know the the time 16 gain or whatever it might be, and you
Yep.
have to know that that's going to be part of your entire thing. You shift it in there and you work with it. So it's good to have that as a visibility for people that are kind of far away from it. It's not a magic word, it's just a it's just a number
Yeah.
that controls a bit.
Yeah. It looks like this number, but it's just a bunch of little bits, and each bit does a different thing. And so each combination of those bits moves data from one place to another.
Yeah.
Yeah.
Yeah. I mean, so maybe give a feel here as well, like how protected is this stuff in a modern processor? Like would people ever see any of this stuff? Like how much of this would you predict that people listening would actually interact with if they're maybe just even using an 8051 processor? Obviously, it's an old processor, but
If you're doing assembly programming, then you are very much thinking about all of this. Maybe not the individual micro instructions, but you're certainly thinking about the register model. And so oftentimes if you're doing assembly programming, you'll look at the data sheet or whatever you're looking at, documentation, and there will be like, here's the register model of this thing, and it says these are the registers, these are what they're used for, these are the instructions. Each instruction will act on certain registers, and so you'll very much be thinking of that. You might not think the next level down in terms of, okay, what are the actual micro instructions to move something from one register to another, but you will see in the data sheet it'll say, oh, this takes X number of clock cycles, and so that kind of tells you how many micro instructions, or it might be some optimization, some pipelining or something going on, but you're certainly thinking of something very close to this. So
right.
if you
Yeah.
don't understand some of the details, you might be able to get by because you understand the mental model of what it is you're programming. But I think it would probably help you to understand physically what's happening as well.
So the optimizations and the pipelining you're talking about, like again, how much do people see that when they're writing code as well? Like, so that's something that people might think about or people might hear about, but they might not be thinking about as they're writing C code and stuff like that. How do you see that happening?
Yeah, probably not. It's probably not something you're thinking too much about when you're writing code. It even if you're writing assembly code, excuse me. So even if you're writing assembly code, you might just see the result of that as being, oh, this instruction takes fewer clock cycles than it might if you didn't have some optimization in there. I
Mm,
don't know. Yeah, I don't know as a programmer that you'd really bump into that too much, but maybe there's something I'm missing. I don't know.
okay. Well, then how did you? I guess the other thing about optimization, I was thinking about like how did you determine? You know that there's a discrete number of clock cycles that an operation takes. Did you go back and then optimize any of your own processes in terms of like doing that pipelining and doing that in the hardware then?
No, not at all. Actually, so every instruction takes 6 clock cycles on my computer, whether it needs it or not, which means that there
Oh,
are a number of instructions where the last few clock cycles are no ops. And the cool thing though is a lot of people have realized this, and there's all sorts of comments in the relevant videos where people are saying like, hey, you could add an optimization where if you get to the end of the instruction, you could have a control word signal that resets the counter for the instruction cycle. And they're absolutely right. You can do that, and people have done that, and it's kind of cool to see people who take this project, build it themselves, and then do optimizations like that.
yeah. So what does the community look like? I mean, like it sounds like there's community built up around this. What, are people, so people are building their own, are they sharing them as well? Is there anywhere like centrally that people are discussing all this stuff?
Yeah, it's I'm well to take a step back, I'm kind of shocked, I guess, that there is a community around this. It
Why?
wasn't
This is
wasn't
cool.
Yeah, I know in hindsight it's like, well, obviously, I mean, I find it interesting, so why not? But I don't know, I feel like I'm kind of weird. But no, I guess when I started this, I didn't really have in my mind that there was going to be a community of people who were going to be building this.
Hmm.
Which in hindsight, I would have done some things differently, frankly. But yeah, a lot of people have seen these videos and said, "Oh, I want to do that," and they've gone out and they've built their own and done different optimizations.
What would you have done different based on knowing that the community was bigger or going to be interested in this kind of thing?
Yeah, well, one one thing for sure. Well, actually, I guess one question is it's kind of weird that it's on a bunch of breadboards. You know, you probably haven't seen anything else that's takes up 14 breadboards. Um, it's a little bit
that is
unusual.
true. Yes, yeah, I have not seen
Full
that.
disclosure, that's a little weird. Um, and honestly, the reason was I just thought that it was easier to sort of see what's going on
Right.
with it laid out like that versus I don't know. It felt a little bit to me anyway, kind of sort of removed if you draw a schematic in a CAD package and then you spit out
Hmm.
a PCB and you send it off and it gets manufactured and you just solder it up and it works.
Right.
To me, that felt like it's a little bit harder to kind of really viscerally see what it's doing and explain what
Yeah.
it's doing versus
Yeah,
being
there's an
able to like, oh,
accessibility standpoint, I think, as well, right? Someone sees a breadboard and they say, "Oh, I know what a breadboard is.
yeah, I know what
I know
that
what
is. I
wire
can
is.
do that.
I could put that together." Yeah.
Exactly. Yeah, yeah. But that does present some challenges because the reliability is not quite
Because
what you get with the
breadboards suck.
PCB. Yeah,
Yeah.
and
Okay. Yeah.
so that's number one. Number
Yep.
two, there's some other shortcuts that I took, just in the interest of I'm interested in computer architecture and just demonstrating how a computer works and how all this stuff works. Um, one thing that I did like that was really kind of evil is I'm using TTL logic chips. And this is
Uh-huh.
partly because I just had a box of TTL LS, old school logic chips, and it turns out that the outputs of those um, have there's like a pull up, pull down resistor kind of thing on the outputs. So you
Mhm.
can't pull too much current out of the outputs.
Mhm.
And it also happens that what is it? The high level for TTL LS is, I think, 2 volts is the threshold.
Mhm.
So it turns out you can stick an LED directly on the output of an LS chip with no current limiting resistor.
Uh-huh.
And the LS output stage will limit the current well enough. And the voltage drop of an LED is like 2.2 volts. So that's still above that 2
About,
volt
yeah.
high.
Uh-huh.
And it kind of works. And so that's what I did. I've got, I don't know, 50 LEDs or something on this thing. And I just skipped the current limiting resistors because it works.
And then some of your viewers did not, I'm guessing, huh?
Or they used CMOS chips or something that don't have that current limit,
Right.
or I mean, the 2.2 volts versus 2 volt. I mean, you're so close on the tolerances there, or your power
Yeah.
supply isn't
Yeah.
quite 5 volt. I mean, you're just so close to the thresholds there. It's no guarantees, and so yeah, I think it's led to some frustration from people trying to get this to work. So that's definitely
It's like
something I would have done differently.
you're helping replicate the days of computer clubs and how people had to struggle their way through.
Yeah, that's it. It's a little built-in challenge.
Exactly. It's like that Easter
Yeah.
egg that they didn't know about and you didn't know about either.
Right. Well, I knew I was
Be
doing it,
Steve
but I figured,
be
well, no
Steve
one else is going to
Woz.
try to do this. Yeah. No, it's just
Yeah.
just my short-sightedness. I figured, well, who's going to want to do all this? And you can just watch the video. But
Mm,
it's obviously the opposite. People watch the video and they're inspired to want to do it.
that's
So here
great.
we are. People are muddling through, I guess. But yeah, there is a pretty good community on Reddit/r/Ben Eater. A lot of people
Nice.
building it there and talking about it. And because of the interest, I started selling kits. So you can actually buy all
Nice.
the components,
Tell
including
us though,
some.
do you sell the LS chips or which kind of chips do you sell now?
Oh yeah, it comes with the LS chips.
Okay.
It comes with very high quality breadboards. So I try to include everything that optimize your likelihood for success. It also comes with enough current limiting resistors that you can put resistors on all the LEDs, which
That's good.
maybe I would
Yeah.
recommend.
Yeah, and that's an interesting point too, because people that are getting into this, I'm sure, are people that are returning to hardware in general. Like that's a big thing. And
Yep.
then you or I think about like, oh well, yeah, you go to your drawer, you grab a resistor, and then they're like, wait, what's a resistor? And then
Right. Right.
I don't have a drawer with anything in it, and
Yep.
then where do I buy it even? Like where do I even start? And holy crap, I'm looking at DigiKey and Mauser and Arrow and
Yeah.
like all these sites that are just like overloads,
Yeah. Where do I
and
start?
then
Yeah.
right. So that's I think from that perspective, it's really good that there's a kit. Of course, from your perspective, if you short a resistor or two, you get a call at 2 a.m. your time or whatever it is, and
Right.
the usual kit business problems, but
Yeah,
it's
yeah.
not insurmountable.
Yeah,
That's
so
cool.
far it's been pretty good. Yeah, and because I put together I mean, there were a lot of people wondering like what are all the parts? What are the parts? And I had some parts list and some descriptions of some of the videos. At some point I put them all on my website, just a whole parts list. And
Hmm.
I added like Amazon affiliate links because I figured why not? Or like other
Yeah,
affiliate links and yeah, I just started noticing like a lot of people are clicking on these things. Maybe I should try a kit.
that's
And
great.
yeah, the kits have been surprisingly popular. And I send out surveys like 2 months after each kit ships, and ask a few questions and things, and um, also ask people how far they got, and it's a surprising number of people who have built the whole computer and it works,
That's great.
which is
And do you
yeah.
have an idea of like you said like a lot of software people, but are like these students, young people, old people? Like what are your demographics like?
Yeah, I mean it's hard to know. I guess maybe I should ask some demographic questions, but the just anecdotally, it's been a lot of sort of career software people who just are interested in a side project and interested in learning more about the thing that they work with all day. And then
Yeah,
there's also a big contingent of sort of high school, uh, even college students, um, doing it for school projects and or just doing it at because they're interested. And I've even talked with some teachers who are doing it in classrooms.
oh, that is great. Yeah, that's really
Yeah,
great. I was thinking about it like, I think about the kind of courses that I took in college. Like I said, I didn't really get started till college, and at that point they're trying to cover things that are relevant to industry, and like so we're doing things that are like accessible and then clean to grade as well. And like there's so many
right,
things that this kind of kit probably wouldn't fit into, but from a practical perspective of like learning, actually learning, not what schools are in the business of always, but
right,
actual
right,
learning,
right.
and they do their thing too. It's fine. This is like a really hands-on, practical, approachable result, I think. And from that perspective, it seems like a really, really good thing.
Yeah, for sure. And I mean, in hindsight, it would be nice to say that I planned all of this ahead of time, but in hindsight, it turns out to be this pretty powerful project in terms of if you actually get the thing built. As far as I can tell, it's impossible to do it without understanding something about computer architecture by the time you're done.
Yeah. Yeah.
Um,
Right. Right. Or at
it's
least being interested at the end of it too, right? You're like, oh,
yeah,
von Neumann. Okay, now what is this like stuff? Instead of like, uh, like me, I'm like, who are these old people?
right, right.
This
Yeah,
is just another
presumably it sparked
math
some
problem.
interest, but even just to get through it, I mean, it's because it's all on breadboards, and you've got to like cut and strip and bend all these wires, and it's a lot of wires. It's a lot of cutting and stripping and
Yeah.
bending.
Yeah.
It's it turns into a labor of love, and it requires a fair amount of persistence to get through, and it's complex enough that you're basically guaranteed to make a mistake somewhere along the way, which
Oh
means
yeah.
that you're guaranteed to have to do some amount of troubleshooting, which again requires
That's
you
a
to
great skill to learn. Oh my
step
god.
back and try to understand what is this thing actually.
Yeah. Yeah.
That's actually one of the things kind of interesting seeing. Like I mentioned, there's some classrooms that have been trying this, and there's a high school near where I am that's doing it with some kids, and it's interesting to see because some of the kids are, literally they'll pause the video where there's like a clear screenshot, and they'll just literally copy what's on the screen on their breadboard,
Oh,
and you ask
interesting.
them questions, and like, there's not a lot of understanding there. Um, but then,
Is that
it's a
wait? Are they getting graded?
yeah, yeah, yeah,
Aha. Yeah. Okay.
yeah.
Sorry. Keep going.
So anyway, no judgment,
No, I'm not
but
judging. I'm just saying
but
that
then
like that's like the motivational side of things, right? I mean, this is like a microcosm of education and learning and the school systems in general. I think like
yeah,
when
yeah,
you just have a output driven thing, like what I hear you saying is it's almost impossible to just get the answer, right? This is an
right.
ultimate show your work, and also by the way, your work is made up of hundreds of wires, and probably a couple are going to come undone. And you're gonna have to figure out what the hell came undone.
That's right. That's right. Yeah,
Yeah, and
yeah,
yeah, there's almost no shortcut from it. So like, what ends up happening when those kids are just copying the output? What happens to them?
yeah. So I mean, it works for a little while, right? I mean, you can pause the video, you can look at what's on the screen, you can say, okay, I count how many holes over, and okay, the wire goes from this hole to count how many holes it goes to that hole. You put that in. You can do that to a point, but yeah, ultimately, I mean, eventually the thing gets complex enough that it's going to fail in some way, and then you're stuck. You have
Right.
to you
And
have
you're
to
behind, really.
and you get behind and all the rest. But yeah, you
Yeah.
have to step back and figure out, okay, what is this thing actually doing? And even if you get your friend to help or you get some help from the teacher or whatever it is, it seems like you're going to come away with some understanding at least of what a register is or what a register transfer is, or some of these
Yeah.
basic concepts, especially when you get to the scale of the whole computer.
Yeah. No, that's great. I mean, like, so I should, full disclosure, I was the kid copying off the screen at one point. I was thinking like that's how I started out, and
Yeah,
then
yeah.
like, but I think some of it is driven from like, oh, well, I got to get this thing done. It's like a thing I have to do. But like, I think ultimately like I said, it is like a microcosm of all education is like, how do you get people to be interested enough at the beginning, right? That's like and I think the building from the bottom kind of helps a lot, but um, I don't know if you have ideas on how to get people interested at the very beginning to build each element up.
Yeah, I mean, to the extent that I've seen challenges, I mean, in the classroom, it's different. I mean, most people who I interact with who buy the kit, I mean, they're coming in motivated. They want to,
Hmm.
you know,
Yeah.
they're not buying a computer build your own computer on breadboards kit on the internet if they're not interested in it.
They're
So
not using it to do their taxes or word
right,
processing. You're
right,
saying?
exactly, yeah. Um, so, but yeah, in a classroom environment where there's the motivation's a little bit more extrinsic in terms of a grade. Um,
Hmm.
one of the challenges certainly is that motivation, and that's a tough nut to crack. I mean, that's what the job of teachers is
Yeah.
to
Yeah.
help motivate um, and yeah, I guess my hope is that um, I guess seeing that bottom up, seeing how each thing builds on the next, and if you understand the one thing, you can see how the next thing builds on that. You see how the next thing builds on that, and I guess my hope is that after you've kind of seen that happen a few times, where you can start with something simple that you understand and build a step at a time into something more
Hmm.
complex,
Yeah.
you sort of build that confidence that okay,
Yeah.
even this complex thing is understandable if I go a step at a
Yeah.
time.
The
And
dopamine loop. Like
yeah,
the little
exactly,
squirts of
exactly.
dopamine.
Yeah,
Yeah.
yeah.
Hmm. Well, this kind of leads into the education stuff in general. I wanted to ask you about. I mean, so you worked at Khan Academy, which is obviously very well known for doing educational stuff.
Yep.
What did you do there? Was it mostly the networking stuff you're talking about?
No, not at all. So it's sort of an interesting story how I wound up there. I was like I said, I was doing networking, sort of systems engineering level stuff, and then I had started my own company for a while where I was building, I guess, I don't know, I say networking hardware, but it was really just a, a server running some custom software, doing
Okay.
some fancy stuff. But
Yeah.
but you sell it as a hardware thing, and anyway, um, but anyways, this network measurement stuff that I was selling. And when I was doing that, I stumbled on Khan Academy. I thought, man, this is really great. And I'm someone who I was never a good student, and
Same.
didn't yeah
Yeah.
didn't do well in high school. Got into college, didn't do well there. Failed out of college a couple times. Never finished college. So yeah, education was not something where I felt like I succeeded. And so I guess I've always kind of had this thought that like, yeah, man, the education system really failed me, let me down. Seems like we could do better. Never really had a sense of how to do that. I mean, I got lucky. This was all kind of at the peak of the .com boom, so I was able to easily get a job in the tech industry, and
Hmm.
had kind of an established network and stuff, and had no problems myself. Um, and so I've been fine, but that it always bothered me that the education system just sort of didn't work for me. And
Right.
so when I stumbled on Khan Academy, I was just like, man, this is exactly what I would have needed. Like if I had this when I was in high school, I would have been like amazing at math because I enjoy math. I just
Yeah. Right.
didn't. There were just these gaps in my knowledge that you get one or two gaps in your knowledge, and it just compounds year after year.
Yeah.
And by the time
Yep.
you get to
Yep.
calculus, you just sort of fall down. You can't do it, and it's just because you have these gaps in pre-algebra or whatever.
And then I think that, like you mentioned too, the confidence piece too, right? Like there's so much of that where once you're like, oh, it's all me, it's all me. You kind of start kicking yourself, and then the next thing you might have been able to do, but then you start from that darker place almost, uh, That is a
Yeah.
bad feedback loop, you know?
That's not, yeah. And for me, I just never understood it because I guess I was reasonably confident in my skills in other places because, I was tinkering with electronics, I was doing programming, like I could do things that it
Yeah.
seemed to me were valuable,
Hmm.
but, the academic stuff, it just never, I don't know. I guess I think I just told myself I wasn't interested in it. And
Mm.
like, yeah, I could do it if I wanted to, but I just tell myself like I don't want to make myself feel
Mm.
better.
Sure. Yeah. Right. Right.
But even years later, I was, as well established career and all the rest, I was like, man, I should like go back and like actually see if I know calculus or teach myself calculus. I picked up an old textbook and I just couldn't get anywhere with it.
Mm.
So, it just frustrated me. But then, yeah, stumble on Khan Academy. I was like, oh wow, this is exactly how this should be done.
Mm.
And this was, early days of Khan Academy, and the website, all the stuff was open source at the time. And I, in the process of doing that, stumbled on a bug as I was, playing with some of their stuff, and filed a bug report, and then found out that, oh, this is on GitHub. So I started poking around, fixed the bug, submitted a pull request,
Nice.
and just started contributing that way.
Yeah,
And
that's great.
ended up basically volunteering my time for a little bit, doing some of that, and started by, most of my early work at Khan Academy was creating interactive math exercises, so little simulations and interactive exploration things. And
That's
then
awesome.
yeah, and so then yeah, they ended up hiring me, and I ended up completely switching my career from this whole networking thing into, sort of education and software engineering. And then
That's
as Khan
awesome.
Academy grew, I ended up managing teams of software engineers there,
And
and was there
so,
for about 7 years.
do you know how many people have used like your individual, like obviously this is just a little bit of ego thing. I'm like feeling your ego for you, but like how like what are some of like the numbers we're talking about here in terms of like how many times something like that's been viewed, like a math concept
At
that
Khan
you did?
Academy,
Yeah, I just mean like so you did like if you did like a math module, like you did a sub module of a math thing, and then like Khan Academy's had millions, hundreds of millions, tens of millions. I don't know how many students or people have gone through the modules, but just thinking about like one module you submit and help with being
yeah,
like actually educating that many number of people in the world.
yeah. I mean, the numbers certainly add up. I mean, I think at this point there are over 10 billion problems attempted on Khan Academy,
Oh my god. Okay.
which,
Yeah.
I mean, I don't know how you reason about that.
Yeah.
And obviously, I mean, as the company grew, we hired a content team, and the
Hmm.
content
Hmm.
quality probably got better than some of the stuff I did. But so I don't know how much of that is me,
Yeah.
but yeah, the numbers are staggering, and it's hard to kind
Yeah.
of wrap your head around stuff like that. You just even on YouTube, it's like you put a video out and it gets 100,000 views, and it's like, I don't know, it's just a number. It
Right.
doesn't
It's
feel
always
like
it's always the minutes watch that the minutes watch is like, holy crap, that's a lot of people spending, just consuming time in lives, always hopefully for a good benefit, You're not like a
but it's just it's so hard to like reason about that. And
sure,
I
sure.
don't know, just psychologically, I don't know. There's something like if I'm giving a talk in front of a group of 10 people, like kind of where my head is just so different than if I'm putting a video
Mm,
out for, what do I
yeah.
have, 200,000 subscribers?
Hmm.
Like
Yeah.
like I'm thinking so much more about those 10 people that I'm giving a presentation to
Right, exactly. Well,
than I would think
having a
about a video.
face in front of you is a big thing,
Yeah.
like that's how humans aren't built to interact behind screens or microphones or whatever, so
Yeah. Yeah. Yeah.
it's hard to visualize. But it's good you do it. So what was it like? So what was the eras of Khan Academy? So you were there like pretty early on. You said.
Yeah. 2011, I guess. That's when I joined,
Mm-hmm.
late 2011.
Mm-hmm.
And
I don't remember when it started. Sorry.
yeah, that was pretty early. So
Okay.
I think there
Okay.
was, maybe 10 people.
Okay. Oh wow. That's yeah. That's pretty early.
Yep.
So what else did you? So you ended up doing like educational planning and stuff like that. Like, did you get into like the theory of education and stuff, or what was that?
A little bit. I mean, so initially, like I said, I was building these like interactive math modules, and just, essentially creating math content, um, because at that sort of early stage, a lot of that stuff was done in software. So we didn't have a team of content creators writing math questions, for example.
Oh,
We'd have software that would write math questions. right? So
Right. Right.
you'd have a random number generator that would, if you want to, I don't know, if you want to do addition problems, you pick a random number, pick another random number, and then what's this number plus that number.
Right. The
And so
computer does it behind the scene, and then the human does it in front of the screen, right?
yeah, exactly. And compare the two, and if it's right, it's right. Yeah.
Right.
So I was doing a lot of building those things from software, and so you build these like modules that would generate, and you could generate an arbitrary number of problems. And it gets a little more complex if you're doing like factoring polynomials, because you have to make sure that the answer works out cleanly and all the rest. But yeah,
Yeah.
building all that logic. And then as the company grew, we hired former teachers and tutors and professors to write math problems. And they were frankly a lot better at it than I was. and then my role kind of shifted more towards building the software that the content creators would use to write the problems.
Right.
And so it
Right. So
was
it became
more
like a content management system at that point, almost
exactly,
like
yeah. We ended up building a whole content management system that handles all of that. And so that was sort of my role shifted more towards like pure software engineering. And then as the
cool.
company grew, ended up managing teams that did that.
That's really cool. I mean, like what I mean, what was it like working there, like from a company culture worthwhile? I mean, like, did people think about the impact it was having? Was that like a big piece of
Oh
the
yeah, yeah.
everyday talk
It
around
was
the
a huge
office?
piece.
Yeah.
That is, yeah, that is 100% what everyone was thinking about. And so there were always like really fascinating discussions about education theory and all the rest going on. Um, and it's kind of interesting being at a nonprofit tech company. Um,
Yeah.
and it selects for a certain sort of person, I think,
And
because
what kind of person is that?
well, I mean, it's a tech company, and in a lot of ways, it felt just like a tech startup. Small group of people building software, putting it out on the internet for millions of users. It's all the things you would do at a sort of typical Silicon Valley startup, but it's a nonprofit, so you don't have this lottery ticket of stock options in your
Right.
back pocket, and
Right.
so that filters out a lot of people, right? Because a lot of people go work for a startup because they want to make a bunch of money, whereas I think people who want to work at Khan Academy want to work there because they want to have some impact in education, and
Yeah.
they see the potential to do that. And so when you put a bunch of those people together, it's a really wonderful culture.
That's great. That's really great. Does that mean that the fridge is not stocked as well, though? Is that one of the ultimate the ultimate
They do a pretty good
outputs of
job.
that? Okay,
They
good.
do
Yeah,
stock
well,
it pretty. Yeah,
at least they cover that. That's good.
yeah. I mean, they are still hiring from the same pool of people. You have to have to meet some
Right.
baseline
Got to hit them snacks. Got to
expectations.
hit them snacks.
Yeah, yeah. There's snacks.
Yeah. That's great, man. That sounds like a really cool culture. I mean, so how did that impact? How did that roll back into your educational stuff? I mean, did you find that impacted how you ended up making videos about computing?
Um, it's a good question. I think honestly, probably what impacted more was back when I was in working in the networking space. I would teach classes there because I guess a big part of my job was selling equipment to customers that had to and helping them integrate it. And so I was often teaching classes about how new networking technology worked and how routing protocols work and all that sort of stuff. And so when I was doing that, um, I was thinking a lot about education, and I was just sort of interested in education. So I was reading stuff about education.
Yeah.
Um, and because also part of my job was sales, I was like a sales engineer. Um, a lot of I guess the sort of way that I thought about sales was I thought about it as an education problem, which was I have this great
Oh, that's
product that's
good.
going to solve your problem. I just need to teach you why, right?
That's good. Yeah.
And
Right. Yeah, you have to
um,
define the problem space and like actually set everything up and be like, no, no, no. Here's what the actual reality is, and then oh, by the way, this thing that my company charged lots of money for is also the answer.
yeah, well, no, it's more like, well, let me. Here's this thing that my company charges lots of money for. Let me teach you how it works. And as I teach you
Oh,
how it
okay.
works,
Okay.
you're going to see why the thing that it does and the way that it does it and all the rest, like why that's going to solve your problem.
Got
That
it.
was
Got
sort of
it.
how
Okay.
I thought about it.
Hmm.
And so, yeah, when I
So
started
is
reading about educational theory stuff, it all kind of like clicked as like, oh yeah, this makes a ton of sense.
hmm
And so I
Yeah.
think that I think it was more like it came from that to then when I started, volunteering, creating content for Khan Academy. I think a lot of that kind of helped make that content something that caused them to then reach out to me and say like, "Hey, do you want a job?"
Yeah. That's great.
Um, and so then I sort of have, I guess, carried that forward.
What are some of the? Do you have any like references that you can keep going back to on the educational side of things? I mean, this is a personal. I'm personally interested in this stuff, so I don't know if there's any books that you go back to.
There's a few, I guess. Just trying to think of.
Ben is furiously searching his bookshelf.
I am like turning around, looking at my bookshelf, like, what do I
Yeah, that's fine.
have?
Yeah, yeah. I mean, like that's great too.
I mean, Mindstorms is definitely a really good one.
Like
Um,
the Lego thing.
so Lego Mindstorms is a book written by Seymour Papert, and the
Oh,
Lego thing is named after the book.
oh, okay.
That gives you some indication of the
Yeah,
what the
that's a
book. So
that's a ringing
that's a good one.
endorsement. And
Yeah.
that's just about like what like the thought process behind like how like thinking happens, or what does Mindstorms really refer to?
So one of the things that Mindstorms introduces is it introduces the Logo programming language.
Okay,
So you've probably come across that little turtle that you program
I don't
in
think I
it.
have actually.
Oh, so Logo is this. I guess it was like an old Apple II. I don't know. When I was a kid, it was a thing, but it's a programming language that you have a little. They called it a turtle, and you would tell the turtle what to do. So you could tell the turtle to walk
Oh,
forward. You could tell the turtle
nice.
to turn left, and then you could tell it to like lift pen or lower pen. And so by telling it to walk forward or turn left, you can draw things.
Yeah.
And then if you want to turn right, well, that's just turning left 3 times.
Uh huh.
So you could write a subroutine called turn right that is just like turns left 3 times. And so from that, they build up this, essentially this whole drawing environment, and you can program all sorts of stuff. So that's one of the things that was introduced in Mindstorms, and just kind of talking about, um, using that to learn about geometry and I guess teaching children programming.
That sounds like that's a little more hands-on than I would have guessed, actually, with the Mindstorms thing. So you were able to basically take that and then kind of back calculate that to how you would use that for teaching methods. Is there like a teaching method kind of written around that as well
Yeah,
in the
that's what
main
a lot of the book
Mindstorms book?
talks about. So it talks about this language and why this language is so powerful.
Yeah, that kind of like sounds like you're really building from building blocks up, and that sounds like a and each of them is pretty graspable. I like the tangible model of like a turtle as like a visualization as well. That's
Yeah.
really good. You could have like Bitey the 8-bit byte that goes through your the computer or something. You know?
Sure.
And now Bitey, now Bitey,
If I
you
ever
go
do
into the
graphics
instruction.
display,
Yeah.
if I ever do graphics display, that's what I'm going to do.
Yeah. Okay. Yeah. Or whenever I think about like campy visualization, I always think of like that thing in Jurassic Park, like Dino DNA.
Right. Exactly.
Yeah. Any other education books that you liked when you're getting into that kind of thing?
There's some interesting ones that have come out more recently, like Mindset by
Okay.
Carol Dweck, talking about kind of the difference between a growth mindset and a fixed mindset.
Oh, that is a. Can you explain that topic? Because I think that is like one of the most important things. Especially like I read that
Yeah.
in the context of teaching adults, and
Uh-huh.
that's like it's teaching children and teaching adults. I think like those are really important mindsets.
Yeah. And well, Mindstorms is primarily around teaching children.
Hmm.
But yeah, mindset, this idea of a growth mindset versus a fixed mindset. The idea there is that a fixed mindset is one where um, it's kind of about the beliefs that you have. So you might have this
Yep.
belief, for example, that I'm not a math person.
Yep.
And I think that's a belief that a lot of people hold, or I can't learn math. And that's a fixed mindset because it's like I can't do that. Whereas a growth mindset, you would have this belief that maybe I can't do this math thing now, but I believe that if I, apply myself and focus and have a plan and kind of work on that plan, I'm going to be able to do that.
Right.
And the difference is that people, and there's basically the book kind of goes through a lot of research about um, how people that have that fixed mindset are don't have as much learning, don't have as many learning gains, or don't show as much in terms of learning gain as people that kind of have that growth mindset. And then the other interesting conclusion of the book is that a growth mindset is apparently something that can be taught,
Yeah,
which
right.
is really
Very
powerful.
meta.
Yeah. And so there's this idea that people, even people who have a fixed mindset, if you can teach them about the growth mindset, show them
Yeah.
some evidence and so forth, that's obviously a really powerful thing. And so there's a lot of work, and that's actually something that we're focused a lot on at Khan Academy, is ways of integrating kind of meta cognition stuff,
Hmm.
sort of teaching about teaching or teaching about learning. For example, teaching about the growth mindset, within the Khan Academy product. Are there things we can do to to kind of help our learners understand that
Yeah.
there is this ability, even if you don't think you can do this thing, a shift in mindset can help you kind of get there.
Yeah, it's almost like a behavioral psychology kind of tied into all of it as well. Like it's an interesting field. Like
Yeah, for sure.
um I think about that when the dopamine squirts, like thinking about that kind of stuff too. It's like when you think about people, and like gamification kind of ties into it too. It's like as you're building people up, you're building up not just their knowledge, but you're also building up that confidence that that they can handle the tougher problem. Um,
Yeah.
and kind of keep going forwards, and that kind of ties back into the growth mindset as well. It's like no, I can figure out that I can do this. It's just a matter of time and persistence.
Yeah. I mean, game designers have really figured this out.
Yeah,
And
it's true.
I think that's what we all aspire to do. I mean, I think it's interesting. Like, one of the classic examples is Mario level one, like the first
Hmm.
Mario first level. Um, just
I'm
the way that
visualizing
that's
all of
laid
it
out.
right now.
Yeah, just the way that that is laid out is just genius, because you start out, there's nothing around you, there's nothing that can hurt you, and you can just walk back and forth, and you can just experiment with that. You can play with that, and you can walk back and forth and get comfortable with that. But then there's this little thing you have to jump over, and then you jump up, and you can take as much time as you want to figure out how to jump because there's nothing that can hurt you. But then when you jump up, you jump over, and it's arranged so that as soon as you jump over, you land right on the Goomba.
Hmm.
And so you see immediately that, okay, if I jump on top of it, like it almost forces you to jump on top of it.
Yeah,
And you can
right,
see right
right,
away that as soon as you jump on top of it, it kills it. And so again, you're safe. But now you've learned that that's how you kill them.
right, right.
And it just, the entire level just unfolds like that. And it's just this amazing thing that you go in, you don't know anything about the game, and the game teaches you how to play the game. And I think that's the holy grail for
Right.
a lot of
And that's without
education
any
is,
like tool tips or like little boxes or like, look over here, you should do this, right?
yeah,
Like, but
if you
it's,
need a tooltip, you failed.
yeah, right. That's,
Yeah. Yeah.
obviously things have gotten more complex, but I think in a best case scenario, like you're saying, it's, you kind of learn all those things as you're accomplishing tasks and moving forward.
Yeah, I think that's the holy grail, is if you could do that for algebra, that would be amazing.
Oh, man.
Um,
Yeah. I think about some of the problems that uh, I encountered in like electrical engineering education, and that I
mhm.
wish I would have had any kind of reference point for. Like the story I always talk about is like having a spectrum analyzer in front of me when I was learning Fourier transforms, or you know, having done a kit like yours before I start doing resistors and op amps and gates and stuff like
Yeah,
building full things before you have to go back and learn the theory. Having that push pull of like hands on theory. Like it's tough to do, but like ultimately that is, I think, the most powerful thing, because when you get to the theory and you run into that roadblock and you have that mindset, like you're saying, the growth versus the fixed mindset, it's
fixed.
not,
Yeah,
yeah, I'm not bad at math. It's I can figure this out because I have to figure this out because I want to make my friggin' computer work.
yeah. That motivation is so important.
Yeah. And so often I think the motivation is just, it's so decoupled from what, it's, we have to get through this curriculum. We have to get through this thing. We have to take this test. We have to, get this thing out there. And if there's no context behind it, then it's really a tough sell, for people that are already pretty exhausted from all the other classes they have doing these things or whatever.
Yeah, it's interesting. One classroom that's they've just started doing some parts of this 8-bit computer project,
Hmm.
and we're right at the end of the school year, so they didn't have time to do the whole thing. But one of the incentives that the teacher said was, if you build a working ALU, so you've got two registers that you can load and you can add and subtract, and you have a clock that can sort of run it. If you get to that point, you'll get a letter grade bump for the course.
Oh, Nice.
That's pretty big motivation, right?
Sure. Sure.
But it's interesting to see. I mean, there's some kids who are already like really into the project, and because they're just into it,
Yeah.
and for them, it's like great free letter grade. I want to do this
Yeah.
anyway.
Right. 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 Right.
And then you got the kids who are motivated by the letter grade, and they're just like dragging themselves.
Yeah.
Uh,
Right. Right. Right.
they're not really into it. They're just trying to get over the line. They're the ones sort of copying what's on the screen and just kind of trying to brute force the thing to the point where it works. And it's I don't know, it's kind of sad in a
Well,
way.
it's almost like like the Dan Pink book I usually refer to on this show that about Drive and based on other people's
Oh
research
yeah,
as well.
yeah, great
Um,
book. Yeah.
yeah, and there's that RSA Animate talk I'll put in here because I always refer people back to it. But it's one of the speeches he gave, and he talks about Drive and stuff like that. But he talks about like money as a motivator, and I think in a school context, like grades are kind of a motivator as well. Like it's obviously there's not a 1-to-1 comparison there, but it's like past a certain point, it changes how you operate in your motivations. It doesn't. It, it's not the true drive there, right? It's not the curiosity. It's not the wanting to learn. It's just the natural output of like having to get this thing in order to progress to the next level, or to make your parents happy, or some kids get their allowance based on grades, stuff like that. Like there's so many like extrinsic motivators that are tough for especially for kids, I think.
Yeah, and I think that's what you have to unpack is like the grade isn't what's motivating you. It's whatever someone has attached to the grade.
Yeah, that's true.
Because
Right.
when when I was in school, like there wasn't anything attached to my grade. Like my parents weren't really that picky, which I think in hindsight I'm probably thankful for because everything turned out okay. And I had time to kind of play and explore. And I think I learned a lot more just in my free time than I
Yeah.
would have if
Right.
I'd been forced to use that free time to drag myself through this homework or whatever that I didn't want to do.
Hmm.
So so I didn't really have a motivation, and so I didn't really have great grades. So I think a lot of it is what is a grade a proxy for, and I think it's different for different kids.
Yeah. Yeah.
But I think the other thing is you mentioned the book Drive. He talks about mastery, autonomy, and purpose,
Yeah.
which I think is kind of an interesting thing if you think about your typical high school kid. Probably isn't getting any of those things because
Um,
there's no autonomy. You're being told what to do. There's
yeah,
maybe not.
some schools are starting to kind of push that a little bit more, but yeah, I think that's more like the charter school kind of like
Yeah, no, and it's
new
great
agey
to
kind
see
of thing.
that.
Yeah.
Yeah, it's great to see that. But yeah, there's challenges around that, obviously. But yeah, I mean, if you don't have that, you don't have the purpose is sort of like, well, I'm doing this thing that's going to get graded and thrown away. It's hard to feel
Yeah.
there's a lot of purpose to that. Mastery, it's like, well, I'm doing something I don't know how to do yet.
Right. Right. So if you don't feel like you're making progress, it's very demotivating at the beginning. So it's again, you have to kind
Yeah,
of build up from there.
yeah. Whereas I think if you're further along in your career and let's say you're a software engineer and you know how to program, you know particular technology really well, you know that you can whatever problem you're bringing your skills to bear on, you have those skills. Um,
Yep.
that's where that mastery thing is very satisfying. I
Yeah.
think it's maybe harder in school. I don't know.
I mean, I think that's a struggle throughout life, honestly. I mean, from a personal perspective, I've been trying to kind of refocus on skill building and stuff like that because
Mm,
I was harvesting skills that I had built up in prior years of my career, and I was harvesting them and using them to make money, of course. But
right.
like there is a true like it's a gift to be able to like just take some time and learn new things, whatever. Like that's from having free time, having monetary stability, whatever. And I feel really lucky to do that. But like that's a big piece, I think, of um, of happiness and being able to move forward with a career. Like you're saying, I think that a lot of advanced people are understand that, but it's the people that are kind of coming up that it's hard to impart that. Like how do you tell someone that that's going to be a thing that's good for them when they're like, well, I just need to get a promotion or get that next job. It's like, oh well,
Yeah, I think
it's
there's confidence though that comes from knowing you can fall back on something or knowing that there's some
true.
some skill set that's valuable. I mean, you know how to lay out a circuit board, for example. Like
Yeah,
if you need to do that, you can do that.
yeah,
Knowing that you have it. Whereas if you come in and you're sort of like, I don't really know anything, um, you can kind of get by for a while, but at some point you want to have some confidence that, yeah, okay, there's something that I know I'm bringing to the table here.
Yeah, it's interesting with the confidence thing too, because I remember like in classes, it was always the people that were most enthusiastic were the people that were obviously they had a good grasp on it in the beginning. And like I
Yeah.
said, I think you said you struggled in school. I struggled in school. I was always really frustrated seeing how engaged they were, and I was like, yeah, but I just don't get it. Like it's just like until you get to that point of
Right,
like
right.
that like little light bulb thing going off, it's like it's a very frustrating experience, especially when you have the social peer pressure of other people clicking with it. And so it's like kind of getting over that first hump and clicking and maybe and hopefully even teaching other people. I'm sure that there's, elements of that as well. Of like, let me help you show you what I've learned, that kind of thing.
Yeah, and that's a cool thing to see in some classrooms now where if there's kids that are going ahead, it's pairing them with kids who haven't yet mastered the thing that they know and
Right. Right.
having the one teach the other. That's because then you learn it at a whole nother level when you're teaching someone else. But
Totally.
no, I don't know. Yeah, I think when I was in school, I mean, my defense mechanism was just telling myself I didn't care.
That's the Fonz method, I think,
Maybe
right?
wasn't great. I don't know. I don't know if I recommend that, but
Yeah. Cool. Well, where do you see yourself doing education stuff in the future? Are you, obviously you're an online teacher. I mean, you're doing more videos and stuff like that? What else are you planning to do?
that's a really good question. Yeah, I'm making more videos. Unclear where I'm going to go with that next.
Okay.
I've been doing like a little mini series on data reliability and CRCs and
Yeah.
how the math behind that works and how the hardware behind that works.
That's cool.
Yeah, so finish that up, and then I'm not really sure where to go next. I know a lot of people want to see me build make the 8-bit computer, add a monitor to it, add a keyboard to it, make it more complex. I don't know how I feel about that. I think it's, like I said, for a bunch of breadboards, it's probably about as complex as you want to get before it's
Right.
just not going to be reliable.
Right. Just still make it accessible so that people could make their own and it'll work actually, Yeah.
But I don't know, maybe get like a 6502 or something and build something from that, a little more complex computer, but start with a CPU.
That's great.
I don't know. Yeah.
Where can
ideas,
I was going to say, where can people suggest ideas? Because there's one thing people on the internet doing is loving telling others what to do.
Yeah, over on the Reddit, it's a good place. Or
Okay.
Video comments, I'll read those often.
Okay. Are you on social media at all? Otherwise?
Yeah, I'm on Twitter, Ben_Eater.
Okay. Awesome. And we'll link all that stuff in below. Ben, thanks for talking about all this stuff. I mean, I think the 8-bit computer is like I said, a good microcosm of the education system, and I really like that you break it down for everybody and make it accessible. That's a super awesome thing.
Yeah, thanks a lot, Chris.
All right, we'll talk to you soon.
Yeah, thanks.